In this lesson, we'll show how to find the moment of a force about an axis, and we'll do so using a vector analysis. For example, when you push on this handrail, you create a moment about an axis that passes through its supports. But since this moment is rather difficult to obtain, using a vector analysis is really the best way to figure it out. And this is always the case when the geometry in 3 dimensions becomes rather complicated, such as this. So let's formalize a way in which we can go about using Cartesian vector analysis to solve the problem. To do so, let's consider this pole, which is subjected to a force F on the arm. Let's say I want to find the moment of the force about the axis of the pole, or about the AA axis. One thing I could do first is to find the moment of the force around point O, which lies on the axis. I'd extend a position vector r to the line of action of the force, and of course then I would create the moment. M sub O is equal to r cross F. Now this is not the moment we need. We need the moment that's projected onto the axis. In other words, this component, M sub A. In order to get it, we'll define the axis direction using a unit vector, U sub A. And then we can use the dot product in order to find our projected vector. So in other words, we've done two vector operations. We've first done a cross product to find a moment of a force around a point, and then we use the dot product to project that moment onto the axis. I can write these two operations in one single equation. And it's called the triple product because it involves the vector multiplication of the unit vector that defines the axis, the position vector that goes from a point on the axis to any point on the line of action of the force, and of course the force vector. Now in order to apply this equation though, if you expand it out, you can set it up as a determinant. And this is what you would write in place of this. When you expand this determinant, you get the magnitude of the moment, M sub A. In the first row go the xyz components of the unit vector that defines the axis. Here is the position vector going from any point on the axis to any point on the line of action of the force, and down here, of course, goes the components of the force vector. Once this determinant is expanded, we get a single number, and that number, as I said, gives us our magnitude of the moment projection, right here. Here it is one more time, just to make sure you really understand the idea. Here's an axis about which we want to find the moment of this force. And to do it, of course, we have to define the direction of the axis, and that's done using a unit vector, U sub A. We can make this unit vector either go this way, or you can reverse its sense and make it go the other way. It really doesn't matter. Also, we need our position vector going from a point on the axis to any point on the line of action of the force, like this one, or this one, or even this one. Any one will work when we put it in our determinant and then we expand it to get our result. And finally, down here, of course, are the components of the force as we've stated. And they're found, of course, when you create the force as a Cartesian vector. Let me do a basic problem to sort of show you how this would work. Here we have a force of 10 kilonewtons on this block, and we want to find the moment of the force around the x-axis. Well, of course, we could solve this problem using a scalar analysis. It's rather straightforward, isn't it? If you consider the fact that the line of action of the force is extended down to here, of course, our perpendicular distance to that line of action from the axis is 5 meters. Therefore, the magnitude of the moment would simply be 10 times 5, or 50 kilonewton meters. You can see that it rotates around the axis this way. And if you direct your curl of the fingers this way, the thumb will be directed in the direction of the positive x-axis. And so if we were to represent our moment as a Cartesian vector, we would simply say it would equal 50i. But here we would also like to show that we can do it using a Cartesian vector analysis. And to do that, first we need to find the unit vector for the axis. That would be U sub A. And what would that be? That's I, isn't it? The direction of the x-axis. Of course, you can also use minus I if you care to, but we'll choose I in this case. Next, we need our position vector. You see one? Or perhaps you use this one. That's not the best to use. There's a better one. Do you see it? This one would work. After all, it goes from a point on the axis to any point on the line of action of the force. This one. And we'll use it. It's the simplest one to choose. It's 5J. It's also possible to use one going from here to here. That has 3 components, though. Notice it comes from a point on the axis to a point on the line of action of the force. And finally, we can also use one going from here to here. That has 2 components. So the simplest one is our 5J. Finally, we need our force as a Cartesian vector, and that's simply 10K. Now our 3 vectors are defined, and we can proceed to go ahead and evaluate our determinant and get our result. First row of the determinant goes what? The components of the unit vector, 1, 0, and 0. And in the next row, we put what? 0, 5, and of course 0. The components of our position vector. And finally down here, the components of our force, 0, 0, and 10. Now we simply have to evaluate this and get our result. And to do that, I'll begin with this term. There, of course, we have 1, and we're going to multiply it by the expansion of its minor. So we cross out this column and this row, and we multiply 5 times 10, we get 50, minus 0 times 0. So the result is 50. Next we take this term. Of course, it's 0, so we'll get an answer of 0 when we do the evaluation. But let's just complete the evaluation, just so you see it happening. This, of course, is a negative one. Don't forget the negative sign. So we have 0 here, and now we're going to multiply it by the expansion of its minor. Cross this column and this row. We get 0 times 10, which is 0, minus 0 times 0. So we have 0 here. And finally, one more, this one. So we write plus 0 times the evaluation of its minor. Across this column in this row, we have 0 times 0 minus 5 times 0. So again, we get 0 here. When you do the evaluation, you get your result. And of course, it comes out to be plus 50 when you're done. And this would be in kilonewton meters. We see that our answer is positive, and because it is, it indicates that this vector, the one along the x-axis, is going in the positive UA direction. Notice that if I had chosen this unit vector to be minus I, then that would be minus in here, and we get a minus answer. And that would indicate that the moment along the axis does not go this way. It would have to go the other way. If I want to express my moment as a vector, I simply would write it as a product of two things. And that is, it would be its magnitude, which of course is 50, and then its direction, which is defined by the unit vector of the axis, of course. And then we would close the braces and we put down our units. And that would be our result. And so having completed the problem, now we'll end the lesson.